All right, everyone. Thanks for joining today's nTop live session. Today, we're here to talk about field-driven design. We're going to talk about some fields created internally in nTop and some fields we brought from external sources like ANSYS. Let's go ahead and get started. So we're starting off with our bracket that we brought in here, and we want to infill it with a variably dense lattice. How do we do that? Well, we need to create some fields, or we need to bring some fields into nTop. We're going to start out with a field that I made inside of nTop. To start off with, what is a field? A field is a field is data, and in this case, it is data represented by this static analysis that we ran inside of nTop. So at every point on the mesh of our bracket, there is a associated stress value, and we turn that into a field, and we can use that to do different things with our lattice. So we take a look. I took our static analysis, turned it into a point map, and then turned it into a field. And if we take a look at our field, we can see that at every point inside of that part, we have values of stress that are indicated by these colors here. How do we use that field inside of nTop? Before we get there, I want to take a look at these min and max values that I created. And these are something that I think you might find useful if you're ever doing field-driven design. Now, this min value, all this is a min block. So right here, min. You pop that open, you make sure it's a scalar list, and then you can drag in from your point map. If you go to its properties tab, you can drag in values, and it's going to display the minimum, or if you use the max block, the maximum value in that point map. And that's really handy, especially when you're looking at stress data or you just want to know the bounds of your field. Now we have those min-max values, we have our field, we need to get it to where we can put a lattice inside our part. So we take it, we shell it, nice and simple, nice uniform shell, really easy to do. We take that shell, we get the internal volume where we want to put our lattice, and then we put our lattice inside of there. If we take a look, we can notice that this lattice is graded from thicker beams where we had those higher stress values and thinner beams where we didn't. So if we go back to our static analysis, turn that on, you can see we have some higher stress values in these areas here. We can stop looking at him, and you can see at those higher values of stress, we have thicker beams. Really easy to do, really awesome tool for lightweighting to optimize your lightweight design so it still has enough strength. What does that look like? How easy or how difficult is it to do with external fields? Well, it's just as easy, and that's really fantastic. All you need to do is go into your tool, whatever you're using, be it ANSYS, Abacus, what have you, and you need to export your results as a .csv file. You need to get them into that file type somehow. But what is a CSV file? Well, if we look at my Excel sheet here, a CSV file looks pretty basic. It has X, Y, and Z. These are coordinates, in this case in meters of our nodes or our points. And then our D here is the value of stress in this case, because I ran a little bit of a different static analysis inside of ANSYS. And then I brought it into our CSV file. All you have to do is import our scalar map, tell it which units, and then again, turn that into a field. Just as easy to do. We take a look at our field. We can see again, we've got that high value of stress. We have a little bit of remnants from extrapolating. Don't worry about that stuff. But we have a relatively similar field, different values. You can see our minimum and maximum values are slightly different. That's because I ran, it was a different mesh first off, and I ran different static analysis on it. But again, take it, shell it, get that internal volume, and then we can infill it with a variably dense lattice based off of the stress data from that one. So a little bit different density gradient. It's super easy to do, but this is with an external field. If we look into the ramp, which is what you use to drive it, we have our minimum value. We have a value that I specified, which is below our maximum, and I knew our maximum because we did that little block there. And we give it some lattice thicknesses to go between. Now that's fantastic. We have a lightweighted infilled body of our bracket. That's great. That's a lot of what we want to do. We're able to thicken our lattice variably. We have a lighter body, a stronger body than it would be if we just did something like a uniform lattice. But we can take this further. We can take this even further, where we don't need to create a uniform shell. We can create a variably dense shell, or variably thickened shell, excuse me. Now, if we take a look at our shell here, we can see we have a much thicker wall here where this stress value is higher versus up top here where the stress was low, it's much, much thinner. And if we go through our part here, you can see it's changing thickness where the stress is, where way back here we didn't have a lot of stress, so it's nice and thin. But up here where we have those high values of stress, we're able to add in that rigidity by variably shelling our part. You'll notice inside of here, this has a little bit of, we'll call it surface texturing or noise. That's because we're basically using this external field, which is computed from a mesh. It's going to give you a little bit of remnants in those spikes in your values. To fix that, you could just do a really quick smoothing function. I didn't do it in this case, but it would take about 2 seconds to do. Now, what do we do with this? Well, we could put another lattice in it, or another uniform lattice, or we could merge it with our variably dense lattice. So if we take a look here, not only do we have a variably dense lattice that is going to lightweight our part and keep it strong, we also now have a variably thickened shell. So we have a lot of extra strength in these regions and a lot of weight saved in the others. So we were able to optimize the lightweighting of our part in 2 ways, not just one, not just a lattice inside there that we thickened up, but we also changed the shell thickness to add in some extra strength. And you can see using external is just as easy as doing internal. You just have to get it into that CSV format. Any questions you guys have, go ahead and throw them in the chat. I'm happy to answer them. This is what I had to show you today. I hope it gave you guys some really great ideas. Please ask me some questions. Someone asked a question, what keystrokes am I using to move, navigate inside, outside the structure of the part? That is a great question. So if we have our variably shelled and variably latticed part here, I have it selected. So either you can click on its block, or you can actually click on the view of it. And then I'm pressing X to create a section cut, little hotkey. And then I'm just grabbing that little blue indicator there of our axis and dragging around. Really easy to do, lets you view the part really quick, really easy, and see that awesome amount of lightweighting and optimization we were able to do just so quickly and so easily. If there's any other questions, please go ahead and ask them. I am happy to answer. Well, I don't happen to see any more questions filtering in. So, oh, there is one. Someone asked, is the data available? Well, this file will absolutely be posted along with the recording of this onto our website. So go ahead and you can check that out. Once it's posted up there, give us a couple hours or a day or so, and it'll be up there. You can definitely take a look and see just how easy this was for me to create. It only took me about 20 to 30 minutes. How do I change the thickness of the shell according to stress? Fantastic question. Let me show you that. Let's go ahead and turn that view off and look at this view. So if we take a look inside of what I did, again, we have this variably dense shell, variably thickened shell. And I said it was super easy, and I did mean it. All we did was give it the body to shell, and this is our full body here, our full bracket. And we use this variable shell block. And we use that because it makes it a little bit easier on us. And all we did inside of the distance, instead of putting just like a 1 millimeter or a 2 millimeter, we input a ramp that I created. And this ramp function is going to say, using the data in this field, as we go from this value, this external minimum value that I selected here, to this maximum value that I specified. And I specified this value different than the actual maximum value, just because it thickened the shell a little bit better, because there were some stress concentrations at these corners, and I wanted to get it a little bit more even so that we didn't add to that problem at all. And then we tell it thicken from a 2 millimeter shell thickness at the low values of stress, and then put it to a 15 millimeter thickness at those high values of stress. So we're really thickening up that wall. And then it computed this little shell for me. You can see it did exactly what we wanted here at those high values of stress that we had, and then at those low values. Super easy to do, and fantastic question. Thank you for asking. All right. Thank you guys for tuning into this nTop live session. We definitely have some more stuff coming out in the future, Monday, Wednesday, Fridays for nTop lives. Next week, someone's going to show a wonderful example of another way to use external fields. So tune in for that. Again, thank you guys for coming. Have a great day and stay safe.